Hello, welcome. This is another AS Further Maths video, FP1. Now, in the last video, we looked at something called the Agrand diagram and how to calculate an argument from a complex number that we drew on the Agrand diagram. Something with an A in anyway. We're going to be taking it a little bit further today. So we're going to be looking at something that we call the mod arg form, or the mod argument form for long. So it's just another way of writing this formula. So what I'm going to do is I'm just going to recap what we did. We had the Agrand diagram, which looks something like this, where you had the real numbers on the x-axis, and on the y-axis we had the imaginary numbers. I put IM for short. Now, what we always said in that in the last little video, you always start from the centre and you draw outwards in the direction of to the point whatever it was telling you. So a standard function we may have something like this, and that could be called Z1. And Z1 is just a complex number. It could equal x plus iy. Now, don't get confused with this as y equals mx plus c or anything like that, because these x's and y's, they're just numbers. I could have wrote okay, well, z1 therefore equals a plus ib. Okay, they're just numbers. They're meaningless on their own. But seeing as we use x and y quite a lot, and they like to use it and call it Cartesian form, then that's just what you've got to learn, unfortunately. There's no point me writing that A and B, which I find a hell of a lot more easy. I mean, at the end of there is just a letter. So anyway, let's kick this off. So what we said was to find the length of this, we did the mod of z and we called that little r. Okay. Well, I might not have done, but that's the length of it, little r. We said the modulus was x squared, if we correspond to the one over here, plus y squared, and we square root that to get the length of r, because the height was, we said, that was y, and the length was x. And then we said the range of the argument is always between minus pi and pi, up to and including pi, or minus 180 and up to and including 180. Okay, either one of them two, depending. I mean, generally you'd be working in radians for this, and it will tell you. And that was the angle there. That we'll call that theta. Okay. So how can we take this a bit further? Basically, all we're looking at is writing this in a different format that actually includes the angle theta. So to do that, we need to understand what x and y actually are. Now, in the last video, I said to find out when you worked out what r is, because it's just a value, so is x is y and y. We said, okay, well, I went with the thing r times the cos theta equals x. Therefore, theta is equal to the cos inverse of x over r. Okay, and similarly, we could have said as well, tan theta is equal to opposite over adjacent, so this would be y over x, and that equals theta. So therefore okay, so hopefully that made some kind of sense, but I generally use the first method there. Okay, so how can we apply this in the case of finding out the values of x and y? Well, if we look at, so that was how we find out x, so we could say that was sort of an equation for x, yeah? But if we wanted to do this for y, instead of using, so if we still used r and this theta to work out y, we wouldn't be using r times cos theta, because obviously we want to work out y, not x. We'd be using r times sine theta equals y. And obviously, therefore, you could rearrange that to get theta. But for the moment, that was just, the first bit was just a recap. But that's what we're going to work from. So hopefully I've proved to you that x equals r cos theta and y equals r sine theta. I've wrote it the other way around in terms of I put y at the end, but that was just to show you where we were going from. Right, so that's how you work out x and y. Now, it's just a simple case. So if we go back to our original z1, because this is sort of like a simultaneous equation now. And we said z1 at the top was equal to x plus I times y. Now, if we know x is r cos theta and y is r sin theta, we can sub this into the equation. So z1 is equal to x, which is r cos theta, plus I, brackets, r sin theta. Okay, but that's getting close to where we're going from. But what we continue to do is we'd obviously expand that out. So z1 is equal to r cos theta plus I r sin theta. Now, as both of them have got r as a common factor, we can take that out as a common factor. So z1 equals r times cos theta plus I sin theta. And this is something we call the mod arg form. And what that means is the modulus argument form. And now, to simplify it down for you, we've got the modulus here and we've got r. Basically, it's the argument form because we've got the angle, and it's in terms of the modulus as well. That's why we call it the mod arg form. Now, this theta here is this theta over here. Now, obviously, to be able to have this in sort of the correct form, we'd have to work out what this theta is over there. But it's just a simple case of doing what we did before, of rearranging these identities to find theta, because either one would give you the same answer for theta. So it's just a case, as I said, of rearranging them to get theta and subbing it into this equation, and you would get an answer for, or you could work backwards if you wanted. It's totally up to you. But as I said, this little bit of the video was just some theory. What I'm going to do now is I'm just going to rub that off. I'm just going to give you a few seconds to copy it down while I waffle on about random stuff. So we'll just give you a few seconds to copy that down, and then I'm going to move on and do some questions to sort of consolidate this, so you make sure you understand it. But the main thing is kind of understanding this form, really. And obviously in the questions it'll show you why you need to use this form. Okay, so thanks for watching, and well done for sticking through it, and we'll see you in a few minutes.